like the last 15 minutes or something. Anybody have any questions about the homework or the stuff we've been talking about? Did the, yes? Practice problems. Yeah. Okay, yes. So, yeah, so all of the problems in like in the announcements, when you see like the assignment for the day, the problems it's referring to are always in the practice problems. And if you get stuck, there's solutions to most of those problems, also in D2L. And you're never turning that stuff in. You're just getting ready to do those problems on quizzes, and mostly you're just trying to learn that material for the exams. Okay. Anybody have any, I think I assigned a couple of those problems where the thing is moving and you have to choose a certain zero position and positive direction, and then based on that, draw the position versus time graph. Anybody have any trouble with those? Those usually give people some headaches. Yep. What? Yeah, sure. You have a preference? Or I could make one up too if you want a different one. Okay. Okay, so let's say, so this is the top of a bridge, and this guy's bungee jumping off of it. With bungee jumping, you probably don't tie it to the ankle, do you? You probably have a harness on or something. This one is to the ankle, though. It's a very cheap company. He chose it for its low price. He has a bathing suit on, and they tied that knot very securely, so he doesn't have to worry. And this is the point where it doesn't look like it from the drawing, but this is where the bungee cord is all the way tight. And this is the water. And so I guess we need some distances. How high is a bridge? A bungee bridge? 20 yards, 20 meters. So let's say the bungee cord, this is 15 meters, and this is 5 meters. And the jumper goes from the bridge to the, I don't know, tight point. Then he goes not all the way back up to the top of the bridge, but let's say he goes up 10 meters. And then back down, and the bungee cord breaks, so he goes right back down to the water. It's fine. He thinks it's fun. Okay, well, I didn't give any time, so let's just don't worry about the times. Well, should I? How long would that take? He goes here. No, let's not worry about the times. And what we want to do is draw a position versus time graph, so there just won't be any numbers on your time axis. And let's say with the 0 position at the bridge and the positive direction, let's do up. Anybody feel excited about the possibility of working on this together before I do it? Could be fun. Or do you feel like not ready to even do it yet? First person who indicates something is going to speak for the whole class. Okay, I'll do it, and then I'll give you one with a different set of like. Okay. Yes. I didn't give any of those, so we're just not gonna. We just won't have any numbers on the time axis. You know what I mean? So we'll just get like sort of a rough shape. You know. Okay, so bridge to where it's tight, up 10 meters, back down to the water. Okay, so I'm going to start by just on a number line showing what the motion looks like. Before I do anything that deals with those choices of the 0 position or the positive direction. So let's say this is the bridge. And then this is where the bungee cord is tight. This is the water. We know that this distance between these two is 15 meters, and the distance between these two is 5 meters. And then we know there's also this intermediate point between where the bungee cord is tight and the top of the bridge. And this is 10 meters. And that's where, after he springs down to where the bungee cord gets tight, then he bounces up 10 meters to this point. Okay, and so the motion looks like this. He starts here. He goes down to here. He comes back to here. And then he goes straight to the water. And that's just with distances and locations. I haven't put any numbers on it. I mean, I put numbers on the distances, but that's not, those distances are, you can't argue with distances. Two people measure the distance between two things. Their measurements are always going to be the same. Okay, but I haven't put any numbers on those positions yet because I haven't chosen a 0 position or a positive direction. But now I'm going to do that. So now I'm going to, it says that our 0 position is going to be at the bridge. So that was given in the problem. So this is 0. And the positive direction is up. That means the positive direction is away from the water, from the bridge. That means the negative direction is towards the water. Okay. And now that we have the 0 position in the positive direction, we can start to put some numbers on these positions. All right, so the guide starts at a position of 0 on the bridge. And then he goes down to where the bungee cord is tight. The distance between the bridge and where the bungee cord is tight is 15 meters, right? And the direction from starting on the bridge, starting at the 0 and going towards the water, that's negative. So he started at 0 and went 15 meters in the negative direction. So what's the numeric label at that point? Negative 15, yep. Then from negative 15, he went 10 meters in the, did he go in the positive or negative direction from there? Positive. So if you start at negative 15 and go 10 in the positive direction, what's your position? Yep. And then he went from, let's see, so he went 10 plus another 5. So from negative 5, he went 15 meters in the negative direction. So where is he there? What's negative 20? Yeah. And now that we have all these, we're just reading these numeric values that we assigned on this motion. So he starts out here at 0, and then the next location we know he's at position negative 15. Then he's at position negative 5. Then he's at position negative 20. Yep.
So why is the positive going to the left?
Because that was given in the problem. That's an arbitrary, or how do we know that it is?
It's up, so up.
Well, I could have drawn it with the bridge over here and the water over here, and then everything would be flipped. The position versus time graph would end up the same. All I did was I put the bridge somewhere, I put the water somewhere, and then up, I know if you're on the bridge, up is the opposite direction of the water. Okay. Yeah. Okay, so the position versus time graph. This is the position. This is the time. And I'll just break the time up into, so how many, we'll like start at 0, and then we have 1, 2, 3 more. So I'll just make it like 1, 2, 3. And if you look at this path, he starts at 0, then he goes to negative 15. Let's mark these two. The important locations for this are negative 5, negative 15, and negative 20. Okay, so he starts at 0. He goes to this location, negative 15. Next, he gets to this location, negative 5. And then last, he gets to this location, negative 20. And so if you draw a line through these points, it would look something like that. Well, actually, it wouldn't. Yeah, forget about it. That's fine.
Would you be so kind as to read the problem for me one time? It's basically just saying the man goes down, he comes up, and he goes down again, and all the intervals for you to decide.
Yes, all the
numbers, all the positives.
Okay.
If something goes up, it goes down, it comes up.
Yes. Okay, so the thing that's totally open for your interpretation of this problem is how you space the time out, because it doesn't say anything about that. So these two you could put close together and then a big gap or whatever. So how much this is squished together, stretched out.
Well, we decided the length, the height of the bridge.
Mm-hmm. Well, the problem, so this is all part of the problem definition. So we did decide that, but the idea is that that's given to you. So all the stuff up through here, we're assuming that's given. That's not negotiable. Okay, so we're told how far the jumper goes, where he starts, where he ends up and goes back to and goes back down, and we're told what all those distances are, and we can't change that. And then we're also told that the 0 is the bridge and the positive direction is up, and so we can't change that either. So now I just made a number line with these 3 locations on them, and the only thing that I had to do for this was I had to have the right relationships between these things. Like the place where the bungee got tight, that had to be between the bridge and the water, right? And the place that he goes up to after that has to be between the bridge and where the bungee gets tight. But I could have flipped this around and everything would be a mirror image. All the numbers would end up a mirror image too. When I finally go to the position versus time graph, it would look just like it does here. So let's do this. I'm going to take this and I'm going to erase all the labels. So we don't know what's the positive direction and we don't know what's the 0. All we know is these distances. And now let's say the 0 is at the water. And the positive direction is, let's say it's still up. Okay? So draw out this diagram of what's happening, including the, so here's just the relative positions and the distances of all these things. This is the motion that the bungee jumper follows. And now based on these, put labels on all these things, numeric labels, numeric positions for all 4 of those locations, and then try to go from there to the position versus time graph, okay? And talk to each other as you do it. You don't have to whisper anything. Feel free to talk out loud, yell, whatever. And if you get stuck, you both get stuck, the person you're working with, ask me or whatever. But I'll give you some time to think about that, see if you can make sense out of it, and then I'll go through it, okay? Okay, so the easiest thing to label is the thing that says 0. 0 at the water. Okay, so that's the easy one. And the positive direction is up. From the water, which way is up? Toward the bridge or away from the bridge? Toward the bridge. So positive is this way. And now to where the bungee is tight, it's 5 meters in the positive direction. So what's the value there? Yep, positive 5. Well, let's do the bridge next. So the bridge we know is 5 plus 15 in the positive direction from 0. So what's that? 20. And then I guess it's, oh, here. So this other point is 10 meters from where the bungee cord is tight in the positive direction. So what's that value? 15. Yes. You did physics. And so now this is the motion of the guy. You know, it didn't change at all when we went to the new 0 and the new positive direction. And now we're just reading the labels as we follow the motion that he did. He starts at 20, goes to 5, goes to 15, and then ends at 0. Okay, so he goes down, up, and then all the way down. And the points that matter to us are 0, 5, 15, and 20. They're all positive this time. 0, 5, 15, 20. Okay, so when time is equal to 0 at the start of the motion, what's the position? 20. Then when the bungee gets tight, what's the value? 5. And then the next place he goes up, what's the value there? And then hits the water, which is the 0. So it looks like this. And it's shifted from what we had before, but the shape is the same. Last time we did one where the shape was flipped over. Why isn't this one flipped over? Yes, exactly. So if it flips if you change the positive direction. So this is, so all of those kind of problems, like the two that I assigned for the last class, you do the same thing, and you can approach it the same way. Draw a line with just the locations on it, draw a path showing the motion, and then based on the 0 position and the positive direction, just label those points. Okay? Is it worth doing another one, or? Okay. Yes? Yes. Sure. Yeah. Okay, so let's just, that one was too much stuff going on. Let's just do a simple one. So let's say there's a house and a dog. No, it's a big dog. And a man, let's see, these are 30 meters apart. And the man walks over man starts at the house. and goes and kicks the dog. Stupid dog. Okay. That's not my best work. Okay. So let's say that walk takes 30 seconds. And now let's say time 0 is 10 seconds before he starts walking. Let's say the 0 position is a house, and the positive direction is away from the dog. Okay, so here's the house. Here's the dog. The distance between them is 30 meters. And the man starts here and ends up here. And we know that the elapsed time is 30 seconds. Okay, so if the 0 time is 10 seconds before he starts walking, and this location occurs when he starts walking, then the stopwatch has already been running 10 seconds before this instant. Okay, so what would it say on the stopwatch? So you start the stopwatch, let it run 10 seconds, and then look at the stopwatch as this guy starts walking. So what would it say on the stopwatch? No, just when he starts. 10. Yep. So this happens at 10 seconds. And then what would it say when he got to the dog? Yeah, 10 plus 30, so 40. So now we've labeled the times at those two instants. Now we just have to label the positions. 0 is the house. So this is 0. The positive direction is away from the dog, so this is positive. That means the dog is 30 meters in the negative direction. So what's the label for the dog? Negative 30. Yep. Negative 30 meters. And so now we can put this together. So the times that matter are 10 seconds and 40 seconds. And the positions that matter are 0 and negative 30. And so the man starts at 0 position at 10 seconds. So that's this right here. Position is 0 and time is 10 seconds. And he ends at minus 30 position at 40 seconds. And so the graph just looks like that. I don't know if that helps. To me, that seems to think about it as a stopwatch and think about like, okay, so if you start the stopwatch, 15 seconds before this event starts happening, starts unfolding, then think about what the stopwatch says at each one of those instants. Any other questions about this? Okay. So we defined last time position, displacement, and distance. So now we're going to move on to talking about velocity. And velocity has direction associated with it. The non-directional quantity that's most related to velocity is speed. And when I talk about velocity, I'm going to break it up into two discussions. The first one is average velocity. And the second one is instantaneous velocity. Average velocity, well, the idea of average speed is like if you have a road trip that takes 2 days, your average speed takes into account all the times you were going over the speed limit and all the times that you were stopped and everything. And so that's the idea of average velocity. Instantaneous velocity is the velocity just at a single instant, like the instantaneous speed is what you see on your speedometer at a single instant. Average velocity, I'm going to start by talking about that, but it's really not going to be very useful to us. The only reason I'm going to talk about it is because it's sort of a stepping stone for me to explain what instantaneous velocity is. So this is almost in every case the one, when we talk about velocity, we're talking about instantaneous velocity. Unless you're specifically asked for average velocity. So later problems will ask for just the velocity of something. It won't say which one of these. It's always talking about instantaneous velocity. And this discussion is really just sort of for background. If you want to go back and try to understand sort of what velocity means, that's what this is for. You're not going to use any of these equations that I'm giving you. I'll give you a set of other equations that you're going to use instead. So this is kind of just to add confusion. I didn't want to say it. Okay, so the average velocity between instants T1 and T2 is, so I'll write this as V average, and it's equal to the position at T2, position at the later instant, minus the position at the earlier instant, divided by the elapsed time. So divided by T1 minus T2. T2 minus T1, sorry. And so another way you can think of that is the displacement from T1 to T2 over the elapsed time. So the meaning, if you have a position versus time graph, so say there's the position versus time, and let's say this is the instant T1, and this is the instant T2. And that means that this height here is the position at T1, and the height here is the position at T2. Then draw a line from the position, from the coordinates at time 1 to the coordinates at time 2. So let's see. Okay. So that's, anybody need me to slow down, go back and explain what I have here? Yeah.
How much is divided by how long?
Yes, that's right. With the extra information that it can be positive or negative, depending on whether it's moved, its net movement has been in the positive direction or the negative direction. Then the average velocity is the slope of this line. So if that line is clockwise from, well, if it's horizontal, what's the slope of a horizontal line? 0. And what that would mean, if you have a horizontal line between those 2 points, is that the position at those 2 instants are the same. Okay? So it hasn't gone anywhere between those 2 instants. It could have gone somewhere in between, but it's at the same spot at both of those 2 instants. And so its displacement is 0 and its average velocity is 0. Okay, so anytime you start and end in the same spot, your average speed can be non-zero, but your average velocity has to be 0 because your displacement is 0. Like, did you know that in high school, I tied the world record for average velocity in the 400-meter dash? Because it starts at the starting line and goes around and ends up in the same spot. And my average velocity was 0, just like Michael Johnson's. Everyone's like, okay, so what if, so that's what happens if the line is horizontal. What if the line is like this one, tipped clockwise from horizontal? Is that a positive or a negative slope? That's a negative slope, and so that means the net motion is in the negative direction. So what's happened in this case is the object, no matter what it's done in between, its net motion is in the negative direction. And then if that line is tipped counterclockwise from horizontal, then the net motion is in the positive direction. So that's how velocity has this. Velocity is like speed, but it also has this directional information attached to it. And it can't ever be vertical. It can't ever be, going this way or this way. Those correspond to infinite speeds. And mathematically, the reason is that if position is a function of time, remember, like when you first started talking about functions in math, you learned that a function can only have a single y value for every x value. Remember talking about that and being like, this is so stupid. Well, for this line between these 2 points to be vertical, you'd have to have two y values at the same, two position values at the same time value, and that can't be. Okay, so now from that, let's talk about what instantaneous velocity is. This is the important one. Average velocity is not that useful to us. So here's the way you find, this is the definition of instantaneous velocity. Choose a single instant now t. Then choose t1 and t2 that bracket that chosen value. So one is on one side and one's on the other side. Okay. So let's do that with let's do this with the graph. If this is P, well, these negative time values don't mean anything, so let me erase those. And T. Okay, so vertical is the position, horizontal is the time. And what I have here is a graph. Position as a function of time is equal to time cubed. And say that what we really want is we want to know the instantaneous velocity at time equals 2 seconds. Okay. So I'm going to start with these two bracketing values. I'll say T1 is equal to 1 second. T2 is equal to 3 seconds. Okay. And now calculate the average velocity between T1 and T2. Okay, so average velocity is the position at the later instant. So that's the position at 3 seconds minus the position at 1 second divided by the elapsed time, 3 minus 1. And we know what that function is in this example. The position is always t cubed. So what's 3 cubed? 27. So we have 27 minus what's 1 cubed? 1 divided by 2. So we have 13. That's the function that I gave. I just defined that. So this is just an example of how you do it. And now the idea is you just keep pinching those two, the T1 and the T2, closer together and see what value it's approaching as they approach all the way to, in this case, 2. So I'll say now repeatedly pinch T1 and T2 closer to T and calculate that average velocity at each one of these new choices of T1 and T2. Then V instantaneous is what this sequence of V averages approaches. Okay, so let's do a few of these with this example, and we'll see sort of how the idea works. Okay, so now so in our first step, T1 was equal to 1, T2 was equal to 3. So now let's make T1 equal to 1.5 and T2 equal to 2.5. Okay. Then V average is equal to the position at 2.5 minus the position at 1.5 divided by 2.5 minus 1.5. And so that's 2.5 cubed minus 1.5 cubed divided by 1. Can someone calculate that for me? I don't have that here. I think I would, but I don't. What is it? Okay, 12.25. And let's do one more. Okay. Now let's choose T1 equals 1.9. T2 is equal to 2.1. Then V average for those is the position at 2.1 seconds minus the position at 1.9 seconds divided by 2.1 minus 1.9. So that's 2.1 to the third power minus 1.9 to the third power divided by 0.2. And what do you get for that? $12.0 what? Okay, 12.01. So this sequence is going, you know, we went 13, 12.25, 12.01, and this doesn't prove where it would go, but you can probably believe that it's settling towards 12. Okay. So if you did this process infinitely many times, that takes a long time. If you kept going, this sequence would approach 12. And so the idea is the instantaneous velocity at 2 seconds is equal to 12. Okay, so let's think about what this means physically on a position versus time graph. So let's say that this is time equals 2. This is 1. This is 3. This is 1.5 and 2.5. And this is 1.9 and 2.1. And each one of these average velocities is the slope of the line connecting connecting those two points that are like pinching on our chosen values. So our first average velocity was this one. And the slope of that line is 13. Okay. Then our second one was this one, from time 1.5 to time 2.5. And the slope of that line was 12.25. And then our third one was from this point to this point. That's a bad color. And the slope of that line was 12.01. So what we're approaching is the slope of a line that's tangent to the curve at that point. So it's tangent to the position versus time graph at that chosen value of t. And therefore, the instantaneous velocity is the slope of the tangent line at t. And for any of you who, you know, we're not going to do any calculus in this class, but if you've taken Calc 1, you know that Calc 1 is all about ways of calculating the slopes of tangent lines. And that's why calculus comes up naturally in physics, because in physics, if your function is position as a function of time, the slope of the tangent line of the position versus time graph gives you the instantaneous velocity. It's an important, it's a useful thing to be able to do. Okay, so here are a few things to notice, and then we'll do the quiz. So important things to notice about instantaneous velocity. The average velocity was defined by two instants. You can't talk about an average velocity without defining two instants. But the instantaneous velocity is defined by that single instant t. And therefore, instantaneous velocity can be written as a function of time. You can talk about an instantaneous velocity at each time. You can't talk about an average velocity at each time because it takes two times. Okay, so therefore, the instantaneous velocity is a function of time. Second, instantaneous velocity is almost the only one we care about in physics. So instantaneous velocity is much more important than average velocity. So if a problem ever says velocity, just says velocity, it's talking about instantaneous. You can always assume it means instantaneous unless it says average. And then third, the instantaneous speed is just the absolute value of the instantaneous velocity. So the instantaneous velocity has directional information that comes from the sign. If you just strip off that directional information by taking the absolute value, it gives you the instantaneous speed. So if your car, well, it doesn't really work with a car because you can go all sorts of directions. But if your train, you can only go two directions in a train. So if your train speedometer had plus and minus, that would be a velocity meter. If you strip off the sign, it gives you instantaneous speed. And then the last thing is the way to interpret that, the sign, the directional information. If the velocity is positive, it means that that instant the object's moving in the positive direction. And same with negative. If the velocity is negative, And at that instant, it's moving in a negative direction. So if a problem gives you a way to know that an object's moving in the negative direction, say, then that tells you the sign of the velocity at that instant. Okay. Here's the last thing I want to say about it. Units. For velocity and speed, it always has units of length divided by time. And so the SI units are meters per second. And so any description of speed or velocity that you've ever heard has a length unit divided by a time. You know, miles per hour is length divided by time. And meters per second is what we're going to use the most. Any questions? Okay. Let me hand out the